Hi everyone. So here the question is, what are the possible issues with gradient descent, right? And the first one goes like this: gradient descent can never converge to the global minima. Right? Now we've seen in the previous video that we've seen about an inequality which says that uh, the function value or the objective function value at the kth iteration and the objective function value at the minima is less than equal to the difference between the initial data point and the optimal point squared divided by 2 times t times k, right? Now this was assuming a constant learning rate t, right? And this actually means this inequality implies that gradient descent converges especially for convex functions, right? So this was for convex functions. So remember in the last video we discussed that one of the conditions for the inequality to hold is that f should be convex and differentiable, right? So it does converge for convex functions, right? So this is definitely a, and for convex functions, right? So typically if the function is not convex, then it converges. So let me write it down. If f is not convex, then the gradient descent converges to the nearest local minima, right? Now nearest to what? Nearest to the initial data point, or the initial chosen data point, right? For the or the zeroth iteration, right? So if this is not convex, then this is what happens. But when it is convex, then we know that there is only one local minima, and that is the global minima, right? So it will converge to the local minima. So this is wrong, right? It converges for convex functions, right? It converges to the global minima, okay, to the global minima. The second one says if the number of training examples is large, then the gradient descent, assuming constant learning, will take a long time to converge. Okay, long time to converge. So we know that what is the gradient of f. So in the previous video we saw that this is nothing but, so this is the content of the previous video. We saw that the gradient is given by this, right? So 2 times x transpose x w minus 2 x transpose y. So 2 times x transpose x to w minus 2 x transpose y. Here observe that we are taking x to be an n by d vector, right, where each row is a data point. Okay, right? So this is the gradient of f, and to compute the gradient we need to compute x transpose x, right? And computing x transpose x is very hectic when the data set is large, right? So this is computationally intensive. So the second option is actually true, right? Because a weight update is only happening once per a data cycle, right? So data cycle means the whole computation of this, right? It involves the entire data set, right? So for one update, okay, what is one update? One update is given by minus, say, t times the gradient of f evaluated at wk. And so one iteration means you have to compute the gradient once, which means you have to go through the entire data set once, right? That is why this is true, because it will take longer. The larger your data set, the more nuanced the gradients become and the more time is used. Yes, this is true, because when the data set is larger, the gradient captures more minute information, right? And the more time is used, because and eventually there will not be much learning, yeah, because compared to the time being used, the learning will be smaller in case of very large data sets. Okay, this extremely large data sets. This is also true, right? This is also true. For extremely large data sets, so for extremely large data sets, the gradient descent backfires, okay, backfires. And this is exactly why we go for online algorithms in the sense, you know, real-time algorithms. So algorithms like stochastic gradient descent, right? Stochastic gradient descent. And what happens in stochastic gradient descent? In stochastic gradient descent, we compute, we iterate, say, k times, capital K times, right? Using only one data point. Using only one data point. What does that mean? That means that the update is given by wk plus 1 equals wk minus t times gradient of fi. Let me write fi wk, right? And what is fi? Fi is of w is nothing but w transpose xi minus yi squared. Okay, so our objective function is the average of this, right? And this is what we use for stochastic gradient. So we do it k times, right? Then we get we get w1, w2, and so on, wk, right? And then we take the average of that, right? So w bar, which we use as the final w, will be nothing but 1 by k times summation of wi. So this is our parameter. This is how we obtain using the stochastic gradient descent, right? Now again, there are various modifications available. There are multiple variants of the stochastic gradient descent algorithm, right? Where instead of using only one data point, we again use some mixture of data points, right? And it can also be shown that in fact, the stochastic gradient descent's estimator is an unbiased estimator of the gradient descent, right? Although we'll not discuss it right now. So this is the a synopsis of what gradient descent does, based on our previous video, which explained the convergence of gradient descent using an inequality.